Okay, we've been talking about this idea of loop shaping using our open loop Bode to and manipulating it with our tools, our poles, zeros, and gains, and reshaping it in order to uh, reshape the closed loop Bode. And last lecture we went through this diagram and talked about what we wanted to try to accomplish in reshaping our open loop Bode. And we came down to a couple of different ideas. In the low frequency, we want to take the magnitude ratio up as high as we can get it. In the high frequency, we want to take it as low as we can get it. We want to attenuate that. And then in the crossover frequency, we want to have a 20 dB per decade slope across our crossover for stability, because that's going to give us a phase margin of about 90 degrees as we cross over there, which is a nice stable system. So this would be a good conservative way to tune or to design a system. Now, another thing you want to watch out for and take in consideration is this initial slope along here also, because if we have a system that has no free integrators and so that initial slope across there is going to be 0, and so our controller, if we want to minimize a steady state error, means we're going to be adding a free integrator, and we're going to have an initial slope in there. Okay. The other thing we want to keep kind of in the back of our mind is this: where is our crossover frequency? Where is this going to be? And we're going to determine that in one of two ways. One, we're going to have some knowledge of some high frequency stuff out there, and we're going to stay away from that by a factor of 10 or 1 decade. Or we're going to design it based on performance and based on some performance criteria, a settling time, a peak overshoot. We're going to determine the omega that we need to accomplish that, and then we're going to set our crossover frequency at that. So with those in mind, those ideas in mind, let's look at an example and see if we can work through and actually design a system based on or loop shaping. So let's take a system. Our open loop is going to be 100 S plus 30. Just a simple first order system. Not too complicated for this case. So our DC gain in this case is going to be 100 over 30, or equal to 3.33. And our DC gain in dB is going to be, then we work that out, 20 log of 3.33, and that turns out to be 10.4. Okay, so we're going to come at 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 0. Let's start up here at 0, 20, 40, minus 20, minus 40. Okay, so up here about 10, at omega equal 1, we have our initial point that we're going to start everything from. And so now we have no free integrators or free S's in this, and so we're going to start with a horizontal line, and our horizontal line is going to come out here to our first pole or 0, which is at 30, which would be right about there. And at 30, we've got a pole, so we're going to break at 20 dB per decade, so that's going to take us somewhere like on this slope. Okay, looking about like that would be our Bode without any controller, our open loop Bode. And our phase would be, let's go 0, 90, minus 90, minus 180. Okay, so this is going to be 0 out to 30, and then we're going to drop to 180. I'm sorry, we're going to drop to 90, and going to have that 90, and we're going to step back 1 decade, forward 1 decade. It's going to look something like this. Okay, and so that's going to be our Bode plot for our G of S, our open loop Bode. So now, if we think about designing a controller for this, there's a couple of things we have to know. We have to know, well, first of all, we could just say, okay, we're just going to do a KP, a proportional gain. And in which case, that's going to allow us to raise or lower this with our gain, which is going to improve our system and give us better performance. So just adding a gain to it would be a reasonable thing, because one thing that I want to point out, this is minus 20 dB per decade. So no matter where we put it, we've already filled that criteria of minus 20 dB per decade, crossing our crossover frequency or our crossover here. And so if we slide this up and increase the gain and have it go something like this, we're still at minus 20 dB per decade. We've increased it, slid it up here, increased the low frequency, and we could keep doing that, keep doing that, increasing it, still satisfying all our criteria of minus 20 dB per decade and having it attenuated at the high frequency. So actually this one theoretically could be solved just with a KP. But we know that there's always a high frequency out there that'll bite us at some point and start creating a resonance. And so we either have to have knowledge of that or have to have some design specs. So in this case, what I'm going to do is I'm going to say, okay, we know there's some high frequency out there, and we know it's at 10,000 radians per second. Okay? Now, another way we could say this, and actually it's very common, we could say something like, okay, there's a high frequency out there and it's at 1600 hertz. Okay, it's very common in the real world to measure frequency in hertz, and so a manufacturer or some instrumentation or some observation may get you a 1600 hertz. In which case we've got to convert to radians per second, because our units of frequency on the Bode plot are in radians per second. Okay, so we have some knowledge of our high frequency. It's out here at 10,000. So this is our high frequency out here. Okay, and so what we want to do in this case is stay 10 times away from that, or 10 times smaller than that. And so what we're going to end up with is our crossover frequency, our omega C, is going to be here at 1,000. And so in that case, if we just wanted to do a proportional controller, what we could do is just simply add sufficient gain so that our Bode plot looks like this. Okay, and we could calculate that gain by looking at this distance in here. That would give us a gain in dB, which we would have to convert to a regular number for our controller. But that would be a reasonable solution to this, just adding a gain to get our omega C, our crossover frequency, up to 1,000 radians per second. Okay, so let's add another criteria in here. Let's say we also want to have minimum steady state error. Okay, so what does that mean to us now? All right, well, if we want to minimize the steady state error, what we're going to do is we're going to want to add a free integrator in there. So what, in terms of our controller, or in terms of our Bode, what that's going to do is that's going to kick us up with an initial slope in here of minus 20 dB. I'm going to start at the same gain here, and so we're going to start. Whoops! Whoa! I lost that completely. There we go. Okay. We're going to start here, and I'm going to run it through the same start point. And we're going to come out here to 30, and then we're going to take another dip in here. So this is going to be minus 40, and then this is going to be minus 20 dB per decade. I'm sorry, minus 40 dB per decade. Okay, I got this all messed up. This is minus 20, and this is minus 40. Okay, because we start with an initial slope of minus 20 from our free integrator, from our controller, and then we add another 20 dB, minus 20 dB per decade pull from our system. So now we're kind of messed up, and we're not on a standard controller anyway. And so if we think about this in terms of a PI controller, what we end up with, the PI is a gain, an S plus Z, and an S. Okay, so if we implement a PI controller, we have a 0 to play with here also. Okay, and so what we would do in this case is we would step back 1 decade from our omega C, and we place a 0 there. So in this case, what we would do is we put a 0 right in here at 100 hertz, and because we start at 10,000, and then we go to 1,000 for our high frequency, 1,000 for our omega C, and then 100 for our 0, and that would kick this back up to 20 dB per decade. And so we would end up with our crossing frequency, and then we would add some gain to this to slide this whole thing up so that this point moves up to our crossover frequency. Okay, now so that would be an implementation of a PI controller on a first order system by loop shaping. Now this is a little bit ugly when you do it with paper. You can do it with paper, but it is much easier to do in MATLAB. So let's go to MATLAB and see what we've got going on here. I've got a controller, and you see, or I've got a system in here. I put our system in here, and I'm in SisoTool. I have all my tools here visible. I have my open loop Bode, I have my closed loop Bode, I have my root locus, and I have my step response. I have all that I need to start doing some design that is consistent with where we are in the class. So we've got good stuff going on here. This is actually amazing stuff. Now we start thinking about our controller and what we want to do with it. And I'm going to get on the Bode so we can do it on the Bode. And first thing we're going to add is a free integrator, or a pole at 0. So I'm going to grab this and I'm going to set this in here, this pole in here. And I'm going to pull up, I'm double click on my C, and I'm going to pull up my controller, and it allows me to set the frequency. And so I'm going to set this at 0. Okay, put it at the origin. All right, so now I've got my free integrator in there, and now I'm going to grab a 0, and I'm going to put a 0 out here at about 100. And oh, look at that. Does that look familiar or what? We've seen that before, right? We saw that when we had root locus design, and now we're seeing the same thing on Bode design. So that's cool. That makes sense. So let's pull up this again, and let's set this right in here at 100, minus 100 actually. And we have now our controller in here. All right, so now with this, we've got our controller. Now all we need to do is increase the gain on it. And now I'm going to do this, and I'm going to be looking at this frequency here. Remember, our phase margin is determined at our crossover frequency. And so if I can push this up the frequency up to where it is at 1,000, then we'll be setting exactly where we want to be. So this is going to be a little time consuming. Okay, a little progress there. Let's push it on up. Okay, and push it on up a little. Oh, I pushed up too much. Okay, I'm at 300, 350, 2,000, 850. I'm going to call that good. 1,100, which is okay. So now we look at this. Our gain margin's infinity, which is good. Our phase margin's at 86 degrees, which is good. We got a nice step response, a little bit of overshoot, fairly fast response. We settle down very quickly, and we have a 0 steady state error for the step response, and we end up with a nice system. Now here's our controller over here. We've got a gain of 11 and a half, and we've got a 0 at 100 and a free integrator in it. So this is our implementation of our PI controller. If we were actually going to implement this into a PID controller, we would want to convert the 0 and the gain to KP, KI, and then put that in the controller, and we would have our system under control. But it verifies what we saw before with the system. We have some stuff going on in the root locus. We have our free integrator, we have our 0 here, and we run our closed loop poles over here, so we get a smaller, a faster time with less overshoot in here. So that would be a simple example of implementation of a PI controller on a first order system. Now, what I didn't show you, and let me back up just a little bit here. Let me erase some of these things. Let me go to the root. I'm going to do this on the root locus because it's a little easier. Erase that. And then I'm going to erase this 0 in here. What I was showing you or talking about earlier, we could just implement this in terms of a proportional gain. Okay, and so I'm going to draw this down. We've got it too high, way too high. Okay, we're getting close. Pull this down, just that's good. Okay, so this would be our implementation for just a proportional control. Okay, we have our crossover at 1,000, and we have a good phase margin. We're not nearly as quick in here, a lot slow response, but it's not bad, and we don't have a steady state error either. But it could be an implementation on some systems depending on what you're trying to accomplish. So that could be a system depending on your criteria. Okay, well, let's move on to some other systems here.